Okay. Thank you to be here for our second session or the second lecture. Do you remember at the beginning of last time, I asked, how many cycles did you see? Did you try to answer me? I already answered. The best answer is always, it depends. That is always not only math, but in our life. No? But in this context here, we will see that really the best answer is it depends. We can see also from here the possible and let me say to justify my possible answer. It depends, but I will come back. I will come back on this later. Let me restart from where we finished last time, but we can intuitively understand now. Huh? It depends on the definition of the distance. Believe me, we are in the presence of three possible cycles. This is also the goal of this course, to show you something which typically, in the basic course of math, I don't know if somebody already have seen such kind of a possible interpretation or the approaches. But anyway, let me come back where we finished last time, and then I will try to clarify why we are in the presence of possible three cycles, even though it's common sense to say or to answer, I see just one cycle. Okay, last time we concluded I think here, but anyway, we restart from here. I am sure that I finished the demonstration here. I think so. I think so. I don't remember if I started with the length or norm of a vector, but anyway, I am sure that the demonstration was done. Before going ahead, nevertheless, let me repeat this definition here very shortly. Last time we introduced the dot product, which is in the form of inner or scalar product. This is defined in this form here, which is the sum of the product of the corresponding component of a vector. Do you remember? Vector equals point. Isn't a definition. Everything is in a definition. This is a possible definition, not the unique one. Now we can intuitively understand that we can have different shape of cycle because it depends on the definition of what? Of length. Let me go ahead introducing the definition of a length and a possible definition of a length, which is based, the first definition, on this dot product. We can understand that the dot product is different. Last time I told you in a possible different dot product. For instance, if I define the dot product as the sum, could be also a different, but let me remain with the sum of not the corresponding component, but the opposite component, the first with the last. Do you remember? I told you the last with the first. Of course, I have a different result. This means the dot product, which it seems to be quite abstract here, plays, in any case, the inner product. About the inner product and the dot product is not clear why could be different. I mean, the dot product is also an inner product, but the inner product is more general because we can understand now, because I can define a different way the dot product. Okay, let me restart from here. Definition of a norm. Length on norm. This means norm equals length, and synonymous. When I say norm, I intend the length. Length, Länge. Definition, the length of norm. This is in a symbol. No? In some books, you can find length of a vector A. Let me say included between these two line left and right of a vector A, which belongs to R up to n. About this nomenclature or definition means just as A consists of n components. If I write, it's difficult. Stop me because very often the mathematics is difficult in the nomenclature, which is in the definition, in a way to explain, a way to write. Therefore, I insist a lot of this in order to show you that math is not difficult, believe me, absolutely. At least my math. Belong to R means, for instance, if n equal 2, you have two components. A vector with 1, 2, or 1, 1, 3, two components which which is included in our table, which define the vector. Is defined as, look, now we can see, if you remember the definition of the dot product, which we use the definition of the dot product to define this kind of norm. Why I speak of kind? Because if I have another definition of a dot product, if I have an inner product, which is not exactly the dot product which I have seen, it could be also really different. I have another different definition of the norm. Very important to notice that the norm is in a scalar because the dot product is in a scalar. I mean, the norm is the root of the dot product. Of what? Of vector dot product itself. But if you think about this particular definition of the norm, what is this? If you remember in, I think, in gymnasium, or probably in elementary school, Pythagorean theorem. Remember Pythagorean theorem? This is the norm which reflects the Pythagorean theorem because it's the root of the sum of the component of the vector. I showed you what I intend. I don't know if you can see this. I show you now with the lateral camera. It basically reflects the Pythagorean norm. But of course, if I define in a different way the norm, the Pythagorean theorem does not work. This means the Pythagorean theorem works just in particular, let me say, the context. This means the distance is defined in a particular way. Now the question is, but is true or that it is not true, the Pythagorean theorem? In math, we don't use really the word true, because never is true. Could be valid, could be not valid. It depends, again, it depends how I define my system, my world. Now we can understand that we can have a different cycles or a different shape for cycles. Again, should I show you that this is reflects the Pythagorean theorem? Or is it boring for you? Oof, it could be that I don't have something right. You have something sticker? Perfect. No, or not. You sorry. I will do that. Because I upload everything. No? I upload everything. Okay, let me switch on the lateral camera. Why does it work? Yeah, now. Yeah. Okay. What I told you is this. This was the first definition of a norm distance, which is characterized by or based on the dot product. The norm of a vector A, this means the length. Do you remember? Norm equals length. If I say the norm of the vector A, probably is too boring, my legend. I repeat always the same thing. Oh, it's okay. Too fast, too slow. But very important, math is in a language. We have a subject, the norm, the verb is, and so on. Believe me, what I am writing here is in a sentence. I try to express with words. Math is not different from another language. The norm of the vector A equals root we know from elementary school, no? Of what? Of the dot product of the vector A with itself. We have seen the definition of the dot A dot B, you remember? And we have here, in the lecture, we have seen something like that. I copied the definition and component, something like that. I don't remember what, but was something like that. Do you remember this? I don't know if I copy exactly. Let me see. Yeah, exactly. I copy. So we have seen the same notation. It's clear, no? Yeah, it's a stage. In some literature, we speak about norm 2, just in the nomenclature. In some books, you can find something like that. In some books, it's not given to because, again, it's in a typical norm. We are working very often with this norm. In fact, we learned that the Pythagorean theorem is true. I would like to say here that Pythagorean theorem is not true in the sense we cannot speak about the true. It's valid. But we have a different, if I say valid and true. We are not speaking about true here. Here, we speak about something valid. Works. Valid means works. It's valid for me, works for me. Okay, let me show you what I intend here. Example, if A is given by A1, A2, let me do a more concrete example if you want. What is the meaning of this definition? Or how I can graphically interpret this definition? We have in math, I am not good about drawing. Is also worst. Excuse me. We can interpret in this form, no? Right? Philip, you stay. Now, in accordance with the definition which I have, what is the length of this vector? Yeah, if you look at this definition, here is the vector A, the norm of this vector A, the length. Remember, norm equals length. Is equal what? Root of A1 squared plus A2 squared. Did you agree, no? Easy. Just apply the definition. This means 3 squared plus 4, which is 2 squared. Let me write exactly. I made mistakes? No, I hope no. Right. This is the length of this. But what is this? Do you remember the Pythagorean theorem? Cathete square plus cathete square root. Huh? It is. But of course, this is based on the definition of the norm which I presented, which depends on the definition of the dot product. Did you agree this? This we will use at the end of this presentation in order to clarify why we have seen, or I told you that we can see more than one cycle. Did you agree with this? Easy, no? Apply the definition. Did you recognize now the Pythagorean theorem? Right. Let me go ahead. This definition of the norm implies, let me say the Pythagorean theorem is in a scalar. We have seen root of 13. Of course, we need to calculate, but we don't in our course we don't need that. Very important. The norm or length is an operator which associates to a vector. A is a vector and a scalar length. We have some properties. I would like to tell you about the property very quickly. Of course, as I told you, the properties must be demonstrated. This is not a definition. Definition, theoretically, we can define whatever we want, but should reflect what we want to describe with this definition. I mean, we have seen that the definition of a norm, of at least this definition, at the end we will reflect in a common sense of the cycle, but not necessarily the most useful cycle. It's a little bit philosophical, but I will tell you now. We don't need to demonstrate the definition. Never. We don't demonstrate the definition. We define. Define, you remember last time I told you, we fix the concept. Define, Latin. We give a finiteness to the concept and a possible definition. Look, properties. Property one should be demonstrated, but it's extremely easy to do that. If I consider the general vector, it's easy to see that this length, this number is always positive or zero in case all elements are zero. If you look why is this positive? Because the sum of square elements is always positive. Now we can demonstrate it also. Let me go ahead quickly, but the properties must be demonstrated. The homogeneity also, I can show you. Do you remember? I defined the product between scalar and a vector. Do you remember last time? The product between scalar and vector, we have a definition. Otherwise, this language here is not clear. No? C multiply A, we have seen. If you want, I show you. Yeah. We defined the multiplication by a scalar. When we are on a definition, we can apply the definition when we need. Do you remember? Using definitions, we build an algebra, a structure which we can quantify phenomena, in which we can make decisions and so on. We will see now, also using the definition and the possible definition of the length, we can build a structure with different concept of cycles. Cycle is in a set of points. Let me go ahead. This means I can demonstrate in general, from a general vector with n components, that the left part equals the right part. I don't do it, but because it's boring, it's extremely easy. You remember, I did last time for a couple properties. Demonstrate means, in accordance with the previous definition, we need a definition of the norm, which is here. We need a definition of the product of the scalar with the vector to demonstrate that left is equal right. This is an identity. The triangular inequality is a property quite important. I put for you here in the line, in slide 12, the demonstration. Again, for the examination, it's not necessary that you learn the demonstration, but here for mathematics, it's very often we demonstrate some properties in some context, but I think this is okay if we look together as this demonstration. This is nevertheless is extremely easy. Let me show you again the demonstration. Now, triangular inequality, probably you learned about that in some courses. I don't know if you remember the meaning of this language here. We have two vectors, a plus b. The sum of two vectors is less or equal the sum of a plus the sum of b. I don't know. This is another way. This is another way to write this expression here. And do you remember in high school, I can square if left and right are positive. I can square the left, I can square the right, and the order remain the same. I don't know if you remember. I mean, 2 is less than 1. No, wrong. 1 is less than 2. This means 1 square is less than 4. But if I write, for instance, -2 is less than -1, square does not work. This we have to be careful in this field.
Hast du bis Viertel vor 5 oder was? Nur ein Block. Von wann bis wann?
Bis Viertel vor 6.
Okay. Dann ist das schief. Ja, okay.
Genau.
Wenn Studenten kommen, dann schickst du die runter in U20.
Ja, U20. Danke. Just to remember a little bit some background in math. Let me show you the demonstration very quickly. Again, 0 if A0 is excuse me, the equality is 0 if A is 0 because or B is 0. What is the meaning? Because if A is 0, we have B equal B, no? If B is 0, we have A equal B, A equal A, excuse me. Sometimes it's easy to write and math than to express with words. Meaning of this triangular inequality. If you think about two vectors, A and B, here we have the length. If you think about, for instance, let me, if you want, let me draw for you these examples in order to understand graphical the meaning. What I would like to demonstrate let me do an easy example. This is the vector A, and this is the vector B. This is the vector. Remember, we learned this. It seems to be that the length A plus B, in accordance with our notation, is less or equals I don't know if you recognize now a little bit better this language, which can be an example, no? But we can do it works for every A and B. Now, just to show you something probably which you know, but for every A and B, it's always valid in the context of this norm, but not true. Valid in the context of this norm. If the norm is different, okay, let me show you this proof of the property 3. If you want, you can look at the proof of the property 2, but it's really trivial. Look at the proof of the property 3. If you consider the second expression, square, I try to clarify a little bit the meaning of the square. I mean how we can apply the square. Something square, this is a scalar. No? Please pay attention. The norm is in a scalar. Something square is equal something multiply something. Please pay attention. This multiplication in our case is not exactly the multiplication which we know from high school. It's the dot. It's the dot. Why that? If you remember the definition of the norm of a vector a plus b is root of the sum. Let me the sum of the component square, right? The root of the sum of the component square. We don't have a root because we have square, norm square. And here we have a vector, let me say C in our case, which is A plus B. This means if this is C, let me consider, we have a C dot C. The dot product replaces, if you want, the product which we know, because the product which we know is the product with the scalars or scalar with a vector. I mean, I don't know if this is a little bit, I try to go real in depth. The norm squared of a vector, C equals A plus B, can be written in this form here. This is equivalent to say C, A plus B, dot C, A plus B. Then, if I apply, we have seen the distributive property last time of the dot product. But if you don't remember, it's intuitive. If you remember a little bit the property in high school or in elementary school, of course, please pay attention. Is the dot, because our elements and not scalar the elements are vectors. Again, A dot A, B dot B, A dot B, B dot A. Intuitively, we can understand that I can write this in this form here. Now I can sum these two elements because I told you about the commutative property in the previous lecture. This means it's intuitive to say that I can sum these two, this is a scalar, this is not a scalar, and this plus this equal 2 times. Please pay attention here without dot. It's not wrong way I put dot, because in the scalar which multiply, another scalar, A dot B is another scalar. Easy, no? Then A dot A is norm square in accordance with the definition, with this definition. A dot A, in accordance with this definition, is norm square. It's difficult, no, it's not difficult. Too difficult. Keep in mind this definition. The definition means, please, this is what I intend. I intend with the word norm, mathematically, something like that. It's valid, it's not valid, it's useful, not useful, forget this at this moment. Of course, the sense of the definition is, it's the possibility to use it. But I can define whatever I want. I can define whatever I want. Now, if I don't use, it's there. If I used in terms of quantification of phenomena, it's better, of course. But anyway, in math, it's not necessary to use everything. At least here in the course, we have to learn how we build tools, how we use eventually possible tools we can build from ourselves. I mean, norm square, if I square this scalar here, isn't a scalar. Huh? I will throw away the root. Do you remember in gymnasium? Square of root square is without square. Without square, without root. Clear, no? Square of root of 2 is 2. I cancel the root with square. This means dot A equal norm A squared. B dot B equals norm of B squared. And then the remainder here. This is difficult here. Now, look, until here, basically, I calculated, I reformulated this expression in this form here. Look now what I have here. Basically, I consider the left part of this expression, because this is the property. The idea is I have to demonstrate, in particular, the property number 3, which the property number 3 holds. This does not means that is true, that means that is valid, means true in the context of the definition of the norm. Valid means true, but in the context of the definition of the norm. Therefore, we say valid. Now, I will consider the right part. You remember, one possible strategy to demonstrate the sentence, in particular, this kind of sentence, which says that the norm of A plus B less or equal norm of A plus norm of B, is to show you mathematically that the left part and the right part have this, let me say, condition, have this order in the sense. Now, let me consider this part here. This left part, I already managed. I transformed. Now, let me consider this part here. What is norm of A plus norm of B, everything squared? If you remember, the distribution, the pseudo distribution of the exponent with sum. I have to do this square plus 2 times this multiplied this. I can also demonstrate it a bit more in depth. If I do norm of A plus norm of B, everything multiply norm of A plus norm of B. Anyway, from here to here, I think I don't need to clarify much. I can do, but in any case, you agree that this right part here can be written this part, if you remember in gymnasium, for instance. Now, we have to demonstrate that this expression here, is less or equal this one. Equal is easy to show. I told you if A is equal 0 or base is equal 0 is the unique case in which are equal. Again, now I would like to show you that this expression is less than this one, but now we have a more explicit expression for the left part and a more explicit expression of the right part. Look, it's easy to see. Why that? Yeah, because if you compare this expression with this expression, this expression here is valid if, yeah, I put the value, the word true, because I copy from a book. True in the context of the definition of the norm. It's not totally wrong. Anyway, he's a famous professor because he considered this norm. If this holds, but we can see this directly from here. If you compare this and this, we can see that this is less than this when A dot B is less or equal norm of A multiplied norm of B. I don't know if it's visible. Again, yeah. I have to demonstrate that this part here is less. Let me consider less now of this part here. This means A dot B must be less than norm of A, which multiply norm of B. We can see what I have to write for you. It's easy, no? Because I can cancel this element here. A dot B less norm of A multiply norm of B. Of course, we have a trivial case in which A dot B is negative. It's always valid because this part here is positive. In case of positive, it's more important for us because we say exactly so. No? Basically, should or the must works this. For A dot B negative works always. But basically, this expression here is equivalent to this one. I don't know if you see it. You remember I told you before, the example is, for instance, 4 is less than 9. If I do the root, 2 is less than 3. This expression here, which is Schwarz equality, which I told you last time, it's basically this. Because if I square this part here, if I square this part here, I have this one. I don't know if you remember gymnasium this. As I told you, this part here, you don't have to learn for the exam. I don't ask, just to show you how a mathematician works, but also the engineer works. To conclude, because we have half hour, no problem. Let me now, it's implicit now what I tell you now. Let me mathematically show you does the triangular inequality implies Schwarz inequality, but not only. We have in the double connection, we can see here, Schwarz inequality, or the triangular inequality implies the Schwarz inequality. We have seen directly now. Because starting from this inequality, we demonstrate already here that if it's valid, the triangular inequality is valid also the Schwarz inequality. See here. If this hold, this means hold with this condition also the triangular inequality, holds also the Schwarz inequality. This means this property here, in this direction, triangular inequality implies the Schwarz inequality, is already demonstrated. Interesting, basically from here to here is already demonstrated. Interesting is to, as the contrary. Yeah, okay, both is trivial in the sense. Yeah, it's trivial both. Really, we have seen this. Yeah, it's correct here. We have seen this because starting from here, I do the root. I have this one, which implies the triangular inequality, but also the triangular inequality implies directly the Schwarz. We can see from here. This means basically we have seen both. Again, this we have already seen if you consider the root of this. But if you consider this element here, which basically implies the triangular inequality, but the triangular inequality implies also this one here, because this directly implies this. Okay, here we have some sentence more, but it's not so important in this sense to go in depth, because we have already seen this here. In any case, we can see here the triangular inequality. Again, I repeat it here. And then if I do this calculation here, if I do this calculation here, and I cancel this, but we already did. Basically, both we already did. Excuse me if the confusion. But anyway, this calculation here, we have already did. I would like to correct the slide to write here, already seen somehow. But here I repeat it nevertheless. This calculations here is what I explained before. Okay, very important now, because we can see also some possible exam exercise. If I have two vectors, A and B, another definition, of course. Very important, both vectors as before when we did, as last time when we did the dot product, must be the same, must have the same number of components. This means should be included or should belong to the same space. About space, I told you, I think once very quickly, but I will come back later. At this moment, let me interpret this notation here, saying that A and B, they have the same number of components. A equals 1, 2, B equals 3, 4. 2 components, for instance, are called perpendicular or orthogonal if A dot B equals 0. Very important. We will use this definition. Again, if inside the definition means if and only if. This means if they are orthogonal, A dot P equals 0. But if A dot P equals 0, then they are orthogonal. Even though in the definition we write just if, but means in both directions. It's closed. The concept is closed. Again, if they are orthogonal, then A dot B equals 0. If the contrary, A dot B equals 0, they are orthogonal. Even though, roughly speaking, we say just if, but inside the definition because we close the concept. Look here, this remark. Did you recall something, this remark? A norm of A plus B squared equals norm of A plus norm of B plus 2 times, as in a scalar product, A dot B. But if A dot A orthogonal B, we collapse here. Did you agree? You remember some property here? We have 2 vectors. As I told you, the norm of 2, you remember here. Show you 1 second. I have a 2 vector, in particular these 2 vectors here, but this inequality holds for each vector A and B. We don't need to add any hypothesis. Triangular inequality. This length less than this length plus this length. Roughly speaking, if from point 0 to point A plus B, I go, let me say roughly, directly, is shorter than I go directly to A and then directly to B, or A plus B, intuitively. But this expression here is exactly what I told you. A and B are orthogonal, right? Look at the picture. This vector here and this vector here, they are orthogonal. It seems. I mean, I didn't tell you before, but assuming that. It seems that in this case, we have this. Do you remember something about that? Pythagoras theorem. Pythagoras theorem. But as I told you, everything in accordance with the dot product defined, as I told you before. You don't believe me? I show you. A in this case is 1, 0. If is 1, 0. B is 0, 1. Assuming that is now in accordance with the definition which I told you before of the dot product. The sum of the product of the corresponding component. This means you have 2 components. No? This means 1, let me do 1 multiply 0, the corresponding component. A1 we multiply by B1. A2 multiplied by B2. Excuse me. A2 multiplied by B2. B2, excuse me, I don't be able to speak today. Orthogonal, right? But in accordance to this definition of the dot. If I define another way, should I do it? They are not orthogonal in accordance with the definition of the orthogonality. I mean, if I define this multiplied this plus this multiplied this, if the definition of the orthogonality remain the same, it means the dot product equals 0. They are not orthogonal. We have two definitions here: definition of the dot, definition of the orthogonality. I try to introduce the word of in this context of the definitions. Which one is good, which one is bad? No, good and bad is not mathematical categories. I feel like we can see which one can be used and which one cannot use. Now it's clear. Could be also not 0. But if remain the definition of the orthogonality 0, they are not orthogonal. Contradicting a little bit what we say if I put the 90 degrees. Let me go ahead. Okay, we have seen here. Yeah, this is another definition, just to because I would like to conclude with these cycles. Basically here, the definition of projection. Projection is also sometimes very important, we will see during the semester. Basically, if I have A and B vectors, again, not 0, this is of course 3. The vector alpha multiplied B equals B dot A divided norm of B squared multiplied B is called the projection of A along B. Now I show you don't have to learn this, I show you in the graphic, so we can understand directly the meaning. If the exam we need the definition, we'll put it. You don't have to keep in mind this, but now graphically I've showed you. Vice versa, the vector beta multiply A, which is quite similar, in which the numerator, basically B multiply A remains, but I will interchange A, B with A here, and the norm square of A in the denominator. Basically, is called projection of B along A. I think I have a picture here. Yeah. Let me interpret this graphical, in which we have in the graphical the projection of A on B, exactly the first one. The projection of A along B. Seems to be complex to remember. You don't have it to remember. If you read it for an example, I will give you the definition for an examination, in the example, just to interpret what I am doing, the meaning of the definition. Because from here, let me consider the first one. The second one is quite similar. Just one I would like to consider. From this definition, it seems to be quite abstract to think that is I have two vectors. That this expression here reflects the projection of A, or it's called, very important, it's called the projection of A along B. And this abstract definition had a possible practical application, or at least I can visualize with this picture here, which it seems to be that this alpha B is the projection of A on B, even though I have to clarify the word projection. The word projection basically characterizes together with this expression here, because this is the projection, alpha B. This definition I didn't define. This means you can ask me, but if we don't know what the meaning of projection, we cannot understand. True, I can say true. projection means, I didn't write, but I tell you, means orthogonal projection. This means exactly graphically that this line here between, let me say, A and the line which characterize B is orthogonal. This is the meaning of the word projection. Because otherwise, what is projection? Projection is exactly that I am considering is in a line starting from B, which intersect the line, let me say 0B. Excuse for starting from A. No? Here we can consider a 0, no, for instance, but orthogonal. Now, to show you that this is exactly the expression of the orthogonal, look how the mathematician works. This is a remark. It's not properties. It's not theorem. But I would like to emphasize this remark because given a definition in math, given a definition, a remark of the definition can help to understand the meaning of the definition. Why we use the could be useful this definition. Look at this. If I consider now A, the vector A which I have, as the sum of C multiply alpha, beta. A and B, they are whatever. But let me consider A in this form here, in which, nevertheless, C dot P equals 0. I mean, C is orthogonal to B in accordance with the definition. Now, look what I am trying to do. B dot A can be written equals B dot A if A is equal to this one. I mean, alpha, whatever. Huh? Now, B dot A, if I do the distribution property, if I apply the distribution property of the dot product with respect to the sum, I have B dot C plus alpha B dot B. But B dot C equals 0. This means I can write this expression here, and from here I will calculate alpha, which, what is alpha? Is the component, or better to say, the projection, as I told you, of the vector 0A. If you want, you remember I told you also this possible definition of this vector A, or the 0A, if you like, on the line on B, if you want to repeat again, or along B, if you want to repeat again this. The meaning of this is A, nevertheless, is a general vector, because A is a general vector, C is a general vector, but orthogonal to B. To be precise, I have to correct here orthogonal projection. But if I don't put in each lecture, we consider orthogonal. If I not specify. Let me see if I can add something here. Okay, and here we can see the connection. I don't know if you remember the connection, the function sine, cosine. In this case, I don't know if you remember the definition of the cosine, in which we can see here from, I don't know if you remember, that A norm of A multiply cosine of theta equals alpha B norm. I don't know if you remember this. Yes, basically, I try to show you exactly this connection. If you want, you can see from here exactly what I told you. This is the definition of the cosine. Or if you want from here. But here probably is more what you need, or what you know already. Cosine of theta, of this angular here, which is orthogonal, is this length here, divided, or basically the length of alpha beta, divided the length of A. I don't know if you remember from gymnasium. You don't need now to repeat everything. And then we can see here, if I basically multiply numerator and denominator by norm of B, from here I have this one. We can see from here, I have this one. Can be written this form here. And at the end, I can write more explicitly what cosine is in terms of dot product. In terms of dot product. Probably we can see also in this form here, which basically reflects again the Schwarz-Cauchy theorem. Just to show you the connection, what we have learned in 10 minutes in gymnasium. 10 minutes to discuss at the end this aspect here, and then we will see next week with 4 hours, 2 blocks, and we will see some exam exercises. We will go ahead, but also with some exam exercises too. Look at this. Again, question now. How many cycles we can see in this picture? The answer depends now, is understandable, because look, here we have the norm L2. Now I need to put these two here because I need to distinguish this norm from this norm from this norm at this level here. The first norm, L2 norm, or let me say the dot norm, because came directly from the dot definition, we discuss a lot. Is the definition. But if I define the norm in a different way, and I can demonstrate that this norm has the same properties, the norm L1 has the same property of the norm L2. I can show you that also the norm L infinite are the same properties of the norm L2 and norm L1. I don't have time to do that. It could be that if I invent a norm, the norm which I invent don't have all properties, okay? If I don't have all properties, this means that the world or the system which I am building with the new norm could be limited, but in any case it's different, could be also more powerful, I don't know. But in any case, they don't have the same characteristics. But I can show you, I don't have time, that these 3 norms, they have the same properties. This means can be applied in the same algebra, but they represent a totally different systems or world. In fact, if I consider the cycle as the point or the set of points with the same distance with respect to a point which we call center, which is the circle. We made this, no? At school. We made this. But the imagination came from a prejudice. I mean, think of more abstract. Don't think about the glue line. Think that a cycle consists, is in a set of points. Each point is characterized by a distance, the same distance with respect to the point which we call center. This way to say characterize at least this is the definition. If I put this in the definition, and now I consider the definition which I told you until now, the first one, L2 norm. At the beginning, I didn't put 2 because I didn't need to distinguish. Now I put different norms. I need to anyway. On the right part, we can see that is the difference, but therefore I need a different notation. If I consider this definition here, clearly the green graphic represents our cycle. Next week, I will show you with some exercises. that if I show you now quickly, and then I do mathematically. But if I consider with the same definition of the circle, the set of points characterized by the same distance with respect to the point which I called center, if I consider the distance now, the second one, I can show you that the circle is not the green, but the red. Because all points on the red, they have a distance equal 1. I can show you mathematically next week. Here is clear from the Pythagorean theory that all these points, in accordance with this definition here, have the same distance with respect to this one. But if I consider this distance here, which is not the sum, the root of the sum of the component squared, but just the sum of the absolute value of each component, the circle is the red one. You believe me? I show you now. For some points, next week I will show you for all points, or at least for this segment, and then I give you the exercise at home to do for everything. For instance, this point here, what is the distance of this point here with respect to this? In accordance to this definition, this is 1 divided 2, let me say x, plus 1 divided 2 y. This means 1 divided 2 equal 1. This means this point here at the same distance like this. But this is not our goal, because we are mixing different things at this moment. The problem which I would like to show you, the aspect which I would like to show you next week, that all these points of the distance equal 1, if this point is 1. Now, of course, in fact, this point here is easy with words to clarify, but mathematically I will show you that all points at the same distance equal 1, as this all point here. Why that? Because this point here, the coordinate of this is 0, 1, right? This means 0 plus 1 equal again 1. This means I show you with words without writing, but next week I will do perfectly. I have here already prepared a slide because I have to accelerate. I'll show you next time. This means this point here, the distance is 1. This point here, the distance is 1. I will show you that all these points, the distance is 1. I have already prepared, otherwise I don't have time enough. Look at this distance here. This means all these black points have the same distance equal 1 with respect to this one, in accordance to this. Did you see? I'll show you. Look, it is the distance of this point here, 1, because I am considering the maximal component of the vector. The vector here is characterized by 1, 0. This means the distance from this point with respect to this point is 1. But all these points are 1, because the maximal component remain 1. Here is again the same distance. And here, when I am moving here, I have it as the maximal component is this here. Basically, this point here is characterized by 0, 1. I don't know if it's clear. This point here is characterized by 1, 1. Did you agree? This means if the definition of the norm is the maximal component, it's 1. Both is 1. Next week I will mathematically show that this is more important to this. The first one is trivial. This is a little bit more difficult to be analyzed. The green is the theorem, the Pythagorean theorem, which is the radius. If I do the orthogonal projection, this squared plus this squared, but in any case, the length here, if this is 1, we have what we call radius. Yeah.
And then Fn is the radius.
L1 distance or L infinite distance. We have also other distance. this is a semi-norm. We use this to detect noise in signals. This means not always the Pythagoras theorem for us is valid, in the sense that useful for us. Depends what we have to get from your analysis for you. I show you next time in a paper from my PhD student, which we give up the Pythagoras theorem. We use this kind of norm in order to detect noise from signals. This means, is Pythagoras true, is valid? Is this norm which called semi-norm because one property does not hold from the property which I presented before? As I told you, not all norms have the same properties. If they don't have the same properties, it is possible to work with this, but we have to take into consideration when we do some calculations. Okay, next time I already prepared some exercise. I show you a little bit more in depth. Then we will go ahead with dependence, independence, and exercise, exam exercise on this topic here. Questions, I am here. Otherwise, next week I will fix my office hour. If the hours are not suitable for us, we can meet nevertheless. You know the schedule. Send me an email. We can meet in the presence or